Right, so today is the second review class for test number 2. Did you have a chance to do all the practice exams online? All right. Well, I will discuss those problems same time. I also give you additional information about about the specific problem. I needed to review some material. Sometimes I give you different methods. You should pay attention. Some problems you can solve it 2 different ways. So the first problem, for this calculus course, we must know the definition for the derivatives and the definition for the integrals. So almost every test, we can put the question about expressing integral as a limit of Riemann sums. Okay. So the first problem is going to be the following, right? Express the integral as a limit. As a limit of Riemann sums. Okay, so here's the integral. Now, sometimes we give an integral which is integrable, then you can find a way to evaluate the integral. But in many cases, I'm not going to give you a problem which can be easily integrated. Like this one. This is the integral of polynomial, but the polynomial is x squared plus 1 to the 9th power. Okay, yes, you can expand it, right? And then you get a polynomial, so you can evaluate integral of polynomial, no problem. But it's very complicated. I don't want to do that. So what I want to do is to express it integral, okay, as the limit of the Riemann sums. Okay, and since the function is continuous, so you can just use the right endpoint. Okay, for this is a formula for continuous function. Okay, as long as function is continuous, and this integral is going to be the limit of this Riemann sum. So for our particular problem, x is going to be 2 minus 1 divided by n. It's 1 over n. Okay, and xi is the right endpoint. So it's going to be 1 plus I 1 over n. So it's going to be, that's it. I cannot simplify it. Okay. So our function is going to be x squared plus 1 to the 9th power. All right. So now, just write down the corresponding limit. Is going to be the limit as n approaches infinity, and this will be xi squared. Xi is going to be 1 plus I over n squared, then to 9th power, and delta x is 1 over n. That's it. So you don't need to simplify it. I needed to see the details, Yeah, this like this. All right. Then we have a bunch of integrals you have to evaluate, okay? Such as 1 to the 4th power, 1 minus 3x, and a 2 square x dx. It's a typical problem. It's a quotient of 2 functions. Okay? You have to express it as a sum of a power function. So 1 over 2 square x, I can take 1/2 out, right, if you want. So x is going to be like this. And minus 3 over 2 is square x. All right. The next step is to find the antiderivative of each term. It's going to be 1 minus 1/2 x to the 1 minus 1/2 minus 3/2 1 plus 1/2 x to the 1 plus 1/2. Okay, and evaluate at 2 endpoints. So we have to simplify. So this is going to be just x to the 1/2, and this will be just x to the 3/2. Okay, when you differentiate, you get what they get the above function. All right. So now you have to put 4 to the 1/2 is 4 to the 3/2 minus 1 to the 1/2 minus 1 to the 3/2. So the second term is 0. Don't worry about it. 4 to the 1/2, and that's going to be 2 minus 2 to the cube, right? It's going to be 8. So it's -6. So that is the answer. There's no other way you can solve the problem. Now there's a possible, if I want to make this problem a little bit more difficult, I will ask you to do the following problem. From 1 to 4, right? For example, square root of x plus 1, 1 minus 3x dx. Okay. I can put 3 here. I can put 3 here. Yeah, that make it easier. Okay. When you get home, do this problem. Okay. Yeah. So if you don't know how to do it, ask or go to Mac. Okay. From 3 to 3. Went from 0 to 3. I just make it a little bit easier. Yeah. Right. So this is a homework. I'm going to put a question mark here. All right. So let's look at number 3. Evaluate this integral. Okay. Now this could be also written as cosine qx dx. Can be show up in 2 different ways, right? If I express it as 1 minus sine square x cosine x, then it's natural to use substitution u cosine x. Now if you use a cosine x, it doesn't work. You have to redo it, okay? So then du equals cosine x dx, and that's good, du, okay? All right, so the integral becomes 1 minus u squared and du. Okay, and then the antiderivative will be u minus 1/3 u cubed. No, there's no integral symbol here, don't. And the plus constant. Okay, which is going to be sine x minus 1/3 sine cube x plus constant. If you use if you let u to be cosine x, this will not work. This does not work. Okay. There is always a problem about find the maximum value, minimum value of the function. Find the absolute maximum and minimum values of a function. So x to the 1/3 on the interval from -1 to 8. Right, so this function is defined on the whole interval. But when you look at this function, what's going on here? When you look at this function, you see that the function is not differentiable when x equals 0. Okay, so you have to pay attention. Note that f is not differentiable at x equals 0. Right. So in order to find the absolute maximum value, absolute minimum value, you just needed to find the critical numbers and evaluate the function at the critical numbers and endpoints. Okay. So, but this observation is very important. Note the f is not differentiable because x equals 0. So x equals 0 is the critical number. Okay, but let's see if there are any other critical numbers. It's 1 minus 1/3 x to the 2/3. I'm going to set this to be 0. Okay, how can I solve it? Right? So how can I solve it? You multiply both sides by, so x to the 2/3 minus 1/3 is going to be 0. Right? And then x to the 2/3 equals 1/3. Well, okay. And you can find, be careful, yeah. 2/3. By definition, this is going to be x to the 1/3 and square equals 1. Okay. Yeah, this is definite. So you can solve it plus minus 1/3 to the 1/2. And then you cube it both sides. So x is going to be plus minus 1/3 to the 3/2. Okay. So this is a numbers in the interval between -1 and 8. So you got two critical numbers. So now you have a critical numbers, x equals 0 and x equals plus minus 1/3 to the power 3/2. After you find the critical numbers, then you just evaluate the function at the end point at the critical numbers. Okay. So that's going to be -1 minus -1, which is 0. Okay, at the another end point, it's 8 minus 8 to the 1/3. 8 minus 2 is 6. Then at the critical numbers. Okay, it's a 0. All right. So how about the negative? Okay, we're going to put negative 1/3 to the 3/2 minus negative 1/3 . Okay, so we have to simplify it. Negative becomes positive 1/3. It's going to be 1/2. Okay. So I need to take some common factor out. I take 1/3 to the 1/2 out. So I get 1/3 here plus 1, which is going to be 2/3. Okay. How big is this number? This number is less than 1, clearly. Okay. So let's look at the next one. Okay. So I will get then I take 1/3 out. I get 1/3 minus 1, and I get negative 2/3. Right. So just the difference is just a sign. All right, so I get 3 values. I get 4 values. Let's go back, right? I got 0, 6, and 1 plus number, 1 positive number. I think this is the smallest value. So the absolute minimum value is going to be f at that number, which is going to be negative 2/3, right? Then the absolute maximum value will be 6, which is at the end point, right? F over 8, 6. So let's go back to this problem. All you have to do, be careful, is to find all the critical numbers. Yeah. Make sure the function is differentiable everywhere. If not, then that particular number is going to be the critical number also. Then you find the 2 critical numbers in this case, and you get total get 3. Then you evaluate it, and you compare the values. Right? Yeah. This is a problem similar to the one I put as exercise at home. Okay, if you're able to do that, then get similar ideas. All right, quiz. That's question number 5. All right. So the region is enclosed by two curves. Y equals x, x minus 1 square, and y equals 0. The location is about y-axis. Okay. So we have to set up an integral for the volume. All right. Step 1, draw the graph. So the graph, when x equals 0 is here. When x equals 1 is here. The graph, we're going like that. Is there any other? I don't think it's going up, going down, okay? So the precise graph will be actually go up here like that. Okay. That's a graph, but the region enclosed by this graph is going to be this region, enclosed by this curve. Okay. We're going to rotate about the y-axis. Okay. So that is the region. You have 2 different ways to cut this solid. Use the horizontal knife, flat knife, or use a cylindrical knife, right? So if you use a horizontal knife, you use a disc to set up an integral for the volume. But it's very hard to find the radius, honestly. Okay, so this function given in this form, you are forced to use a cylindrical shells to set up an integral. Okay, so you draw a cylinder. Okay, that's the inside the cylinder. So this is the radius, R, that is h height. So the volume is going to be 2 pi r h dr. All right. Something, yeah. So this is the volume, right? Volume is going to be integral 2 pi r h dr. The largest, smallest radius for the is going to be 0. Smallest value of the radius is 0. The largest one is going to be 1. If you look at this integral, the only thing you have to do is to express h in terms of r. Okay. And this is a point, right? So if this is a point x and y, and r is going to be x, y is going to be h is going to be y. Okay. And I know y related to x by x over x times x minus 1 squared. So clearly, you can also express h in terms of r, like r minus 1 squared. Okay. If you want to use the r variable, that's fine. So that's going to be integral 2 pi r, and h is r times that. You can also express it as the integral with respect to x. Okay, so we're done. The next question. Okay, and the notation here is about the vertical line y equals 1, or horizontal line. Yeah.
I have to find the value, or I just leave it like this?
Just leave it like that. When I say set up an integral, don't waste the time to evaluate. Set up an integral. I do not ask you to evaluate. Okay, to save time. Otherwise, you're not going to have enough time to finish 10 problems. It is not my primary purpose to test you how to evaluate integral. This is polynomial. You can do that. Okay. So the region is enclosed by these two curves. Its rotation is about the line. Set up an integral, right, for the volume. So probably we have two different methods to solve this problem. All right, so the first one, let's find the intersection. This is y equals x squared. This is x equals y squared. Okay. So that is the region we're talking about. So now it's rotated about the horizontal line y equals 1. I don't have a space. Okay, I'm going to erase this again. I'm going to resketch because it's otherwise there's no space for me to draw the complete graph. Okay, so the intersection point is 1 and 1 here. And this is a horizontal line. You're going to rotate that region around the, around this line y equals 1, right? So imagine you will get something okay. All right, so what I'm going to do, I have 2 different ways to solve the problem. Use disks and use cylindrical shells. It's up to you how to use it. So I'm going to use disks. This is my typical disk. Okay. So using disks, and then the volume is going to be integral of ax dx, and the x is runs from 0 to 1. And then I really needed to find the 2 radius. Okay. So my this is the radius capital R. That would be little r. Okay. So you have to find out what is capital R, what is little r for the given x. So capital R, I think I'm going to use the curve at the bottom. Okay. This is a curve. Y equals x squared. So for the x, the height is x squared. So the radius is 1 minus x squared. The little r is also going to be 1 minus. If I describe the curve here, it's going to be y squared x. Y equals square x, because x equals y squared. So this is the difference is going to be square x. Okay, which 1 minus square x, that gives the radius a smaller disk. Right, so now you can put it in. Okay, that's it. You must draw the picture. Let's repeat again many times. You must draw the picture. You must indicate what is R, what is little, what is capital. Okay. Express them in terms of x. Cannot just put the integral there. Okay. And this partially correct. It's hard to tell this is a correct or not. If you make a bigger machine, right? If your parts is broken, the whole machine will be broken. You cannot run it. So it's equally important. Anyway, it's harder for me to give partial credits if the integral is wrong. If some part of it wrong. Okay. Right. So that's the first. First method. The second method. Okay. But so this time I'm going to cut it using cylindrical shells. So I get a cylinder inside. Okay, that's a cylinder. Cuts, yeah, it's cutting through the solid. So I need the radius R, and here's H. right? So the volume is going to be integral 2 pi r h d r. R runs from 0 to 1. The smallest value for r is going to be 0. The largest value for r is going to be 1. I needed to express h in terms of r. Now, for the same y value, right, in order to get the r or get the h, I think for the same y value, r is going to be 1 minus y. Okay? But the h is not easy to figure out. You have to solve for x using each of the equation, right? Okay, so the one and here, this is y equals x squared. This is be y equals square x, right? Yeah. So for the given y, what is the x value? I think it's going to be, so this one is going to be square root of y, and this will be y squared. Okay, so it's going to be square y minus y squared. Right. So if you don't want to use y variable, then you have to express h in terms of r. So y is going to be 1 minus r. Okay. But if you want to use a y variable, then you have to use substitution here, right? So this is going to be when I equals 0, y equals 1. When I equals 1, y equals 0. 2 pi r. R is going to be 1 minus y. H is going to be square y minus y squared. And di is going to be negative y. Okay. So you can also express in the form. So that's it. This is integral for the volume. If you see the picture, you should be able to express the height in terms of the y value. So the picture is important, you know. Without picture, how do you figure out the radius r and the height h? The next one is about optimization problems. There is always an optimization problem. So it says that a prism with a rectangular base has a volume of 9,000 cubic meters, assuming the length. Okay, let's draw it. So this is a length, this is a width, this is a height. So we assumption is going to be volume is going to be 9,000 cubic units. I also know that the length of the base is going to be twice the width. Find the dimension that will minimize the surface area. All right, so this is a rectangle, right? Essentially, for a rectangle, the dimension involves 3 parameters: length, width, height. But now, because I assume the length is twice the width, so essentially there's only 2 parameters, and the width and the height. Okay, so what we're given is the volume. Volume is going to length, all right? So L is going to be 2W, which is 2W square H, right? This is going to be 9,000. The surface area, let's find the surface area. The bottom part twice of LW, bottom part, top part. Twice of WH, left and the right. And this will be H, right? And the twice of LH, front to the back side. Okay. I replace L by 2W. L is a 2W, so it's a 4W squared plus 4 okay, it's going to 4W squared plus 6WH. We want to minimize this. But we are given 2W squared H equals 900. So H is going to be 9,000. So 9,000 divided by 2H, 2W squared. So I plug them into the surface area formula. Okay, then you simplify. Clearly, this function has an absolute minimum value. The reason is the function goes to infinity on both sides. So there's somewhere in the middle and has the lowest value, as smallest value, yeah. So we find the derivative. It's going to be 8W minus and set this to be 0, then you get 8W squared okay, it's going to be 8 to 7, 27,000. So W is going to be 3,000 divided by 2. It's 1,500 units. So the length is going to be step by step. The length is twice W, 3,000. How about the height? Since the volume is fixed, the height is 9,000 divided by 2 squares, right? 2W squares. Okay, so it's going to be 9,000, 2 times. You can simplify this now. Wait a minute. Let me check. I made mistakes. That's not, there are too many zeros to put there. All right, so this is going to be just 30. Hmm? All right, 1,030, it's going to be 15. That's going to be 30. That's very reasonable. And here is going to be 9,000, 2 times 15, 15 actually I write it in this form, right? So that's going to be, yeah, after simplifying, I get 900 divided by 2, 9,000. So this can be 10 divided by 20, okay? So it's going to be 20. 20 is a reason. Where is my file? Yes. Okay. So we solve the problem. Then we sketch the graph. We have 3 different types of graphs, right? Polynomial, and those with the horizontal asymptotes. All right, so here's the function. Sketch the graph. Find all necessary information and sketch the graph. What I'm trying to show you is it's not necessary to find the derivative when you sketch the graph. But if you want to know the precise location of the maximum point or minimum point, then you should find the derivative and get the values, get the coordinates, okay? So take a look at this function. It's going to be x minus 2, x plus 2 here, right? So what are the intercepts? Intercepts, okay, I think it's clearly when x equals 0, y 0. Okay, there is no other intercepts. Then I write down the asymptotes. The asymptotes could be horizontal, could be vertical. So x equals plus minus 1, there are the 2 vertical asymptotes. Horizontal asymptote must be 0. So y equals 0. This is the horizontal. Why? Because when x approaches infinity and f of x approaches 0. I think I'm going to sketch the graph now. Okay. So nearby x equals negative 1, negative 2. When x equals close to negative 2, the function is going to be about, what I'm going to do is I'm going to keep x plus 2. Okay, it's going to be negative 2 minus 2 here. Okay, which is just 1/2. Okay. So that means the graph looks like this. Okay. Nearby 2, then the function is going to be x minus here, x plus 2, and x. So it's going to be 2 plus 2 is 1/2. Right? So the graph still looks like because the positive constant times 1 over x minus 2. All right, let's combine them together. Okay, by the above data. I actually can sketch the graph. Okay. Okay. So this is a x. That's x positive. Here's x net. So nearby the vertical line x equals -2, the graph looks like that. Nearby the vertical line x equals 2, not a negative. The graph looks like that. And the graph passing through this point. And clearly now you see the picture already, right? Just connect that. There's no absolute maximum value and absolute minimum value. So this graph, yeah, everywhere is decreasing. Okay. And maybe somewhere concave up, somewhere concave down. So before we do a computation, I don't think that we need it. Okay. First of all, this is a derivative is, yeah, this is going to be a negative. Here's the derivative is negative, and here's the derivative is negative. Right, it's decreasing. So I want to say that f is decreasing on the whole line. Okay. I can also tell that the second derivative here is positive. Here the second derivative is negative. Here the second derivative is positive. Here the second derivative is negative. Yeah, so f concave up. Right. And this is f concave down. And this will be positive 0. Okay. So you can tell that, and here the second derivative is positive. You know, we probably don't need to waste time to even find the derivative for this particular problem if you want to sketch graph. But you can show that the derivative is always negative. Let's check that, right? Let's verify this using derivatives. Okay. So let's find the first derivative. Okay. Then minus 2x. The derivative denominator is just 2x. So I would get it's actually is negative 4 minus 3x squared. This is always negative, except for 0. No, nothing about 0. It's true, except for x plus minus 2, because that's where the function is not defined. So that's it. Another story problem is about what then empty the tank, something, right? So let's look at number 9. Let's write down the problem. A rectangular tank with base area of 16 square meters and height is equals 8 meters. In full of water. We needed to find out did we do this problem before? Oh, looks like. Similar problem. All right, I'm going to draw the picture. So this is 8. I know the base area. Area is the base, right? That's all you need. So we're going to bump half of the water to the top. That's one slide. So I have to choose a coordinate system. Right? Doesn't matter which way you do. You can choose. That would be my coordinates. Here's the origin. So this will be 4. That will be 8. Between 4 and 8, all the what should be gone. Should be pumped out. Should be pumped out, right? So the idea is divide this interval into many slides. So delta x is going to be 8 minus 4 divided by n. It's 4 of n. And the xi is going to be 4 plus I over n. Okay. So that is the xi and the xi minus 1. So that's one slide. Okay. The volume of that slide is going to be the base area times delta x. Okay. The force needed to lift that piece is going to be the weight of this part. So the volume times times the density. Okay, that's going to be 1,000 kilogram per square meters times VI 16 delta x. Right. Now that piece is lifted to the top of the tank. The work done for that piece is Fi times I think is going to be 8 minus xi. So that's going to be VI, no, 16. Yeah, the base area is given. I don't know the dimension of the base, but it's a rectangle. Okay. Okay, so that's it. So the total, it's about that, right? The total is going to be I from 1 to n. This is about all right, if you let n go to infinity, it approaches the work done by pumping out of the water. So that's going to be the integral. Be careful, x from 4 to 8. All right. Now you can also use a substitution to simplify it. For example, you can let u to be 8 minus x, du equals negative dx, u equals going to be 4 when x equals 4, u equals 0 when x equals 8. All right, so this integral becomes 4 and 0 1,000, 16,000, right? And then this is u and the negative du. Okay, so if some students use a different coordinate system, coordinate line, you end up with this kind of integral. Right? But anyway, it's going to be half of u squared. Evaluate 2 endpoints. So 16 divided by 2. Okay, so this will be done. Yeah, this will be done. All right. Let's try the next one. This will be the last problem. Yeah, you ask it to find sketch graph, find necessary information. And the sketch graph. Take a look at this function. What's the domain? The when you see radicals, you know, it's not defined for all x. So the domain will be x greater than 0. So it's go beyond that, it's not going to be defined. Okay. I also see that when x, that's going to be negative between, f of x is going to be negative for x between 0 and 3, f of x positive if x is greater than 3. So I get pretty good idea about the graph right now, even. Okay. So the idea is here's 0, here's 3. Okay. That's it, right? So there is a maximum, minimum, absolute minimum value there. You have to find out. You have to use a derivative to find the exact location of the point. And also you needed to know whether it's always concave up. Is there any points of infraction? Okay. So this is going to be x to the 3 over 2 minus 3x to the 1/2. All right. So let's find the derivative, because when you see the picture, you know where is the critical numbers. So that will help you to avoid making mistakes, okay, even in the computation mistakes. So it's going to be 3 over 2 x to the 1/2 minus 3 over 2 x to the -1/2. If you set this to be 0, 3 over 2 will be gone, all right? And the x is x equals 1. X equals 1, somewhere here it's, okay? So when the x equals 1, the y value is going to be 1 minus 3, it's going to be -2. So that would be the lowest point on the graph, right? And the absolute minimum value is going to be -2. So clearly, f is decreasing on the interval from 0 to 1. F is increasing from 1 to infinity. Now, it's not clear to me whether there's any points of inflection there, right? I needed to find a second derivative. Right? It's almost, yeah, it's going to be, I take the 3 over 4 out, I get x to the 1/2 plus x to the -3 over 2. You can, this is always positive, it's always concave out. Okay, x always concave out. All right, so just always concave out. That's it. So we completed the graph, get all the required information. And as you will see, my style is always trying to avoid finding derivative, okay, at the very beginning, and the sketch the graph. Of course, I don't know the exact location of the absolute minimum point, okay, but I can do late, when I have to find the critical numbers and locate them, right? So this is my suggestion. Trying to sketch a graph without finding the derivatives, okay?